Hello, and welcome to the log solving day 3 video. In this video, I'm going to be going through the 4.6 packet and just doing a few of the problems. If you'd like to see more of the problems, take a look at the completed 4.6 notes. Just keep in mind, we will not be doing all of the different types of problems, and I'm also skipping all of the story problems because we're going to spend all day on Tuesday doing that. So we're going to go through 6 problems today. The first problem is on page 3. It's going to be part A over here. So it says solve the following exponential equations, express irrational solutions in exact form, and round to 3 decimal places. So you'll see me use a solution set and then plugging these things into a calculator. So let's start solving. Taking a look at A, I want to be able to rearrange this, but I can't do that with the 4 here. So I'm going to start by dividing each side by 4. So we have 2 to 3x is equal to 5 over 4. And then from here, now I can rearrange. This is my base, this is my exponent, this is my answer. We're going to rearrange this so that we have log base 2 of 5 over 4 is equal to 3x, or log b. And then from here, I notice that this is a base of 2, and my calculator doesn't know how to plug that in, so I'm going to use my change in base formula that we learned in the last video that says that we can do log of 5 over 4, or log of our argument, divided by log of what was originally a base, but now is our new argument. And that's going to be equal to 3x. And then I can divide both sides by 3, however, that's going to give me a triple fraction. So instead, I'm going to multiply both sides by 1/3. That way I can just multiply straight across in my fractions and say that log of 5 over 4 divided by 3 times log of 2 is equal to x. So this is what I'm going to be putting in my solution set, since this is as simplified as we can get. That's as exact as we can go. So this is my irrational solution in exact form that's in my solution set. And then it also wants me to round to the 3rd decimal place. So once I plug this into my calculator, I get that that's about 0.107. And that's the only problem I'm going to be doing on this page. In this problem, I use 2 different rules. It's common to use more than one rule in a problem. Problem B is definitely a challenge problem. We've cut that from this year, although feel free to try it if you like. Problem C, I think, is definitely doable. I think there's just other problems more worthy. So let's try some of those. We're going to be moving on to example 7 on page 5. So if you're following along, we're skipping all those story problems because we'll go over that later. Now we're taking a look at example 7. We're going to do both A and B. So taking a look at A, I see that log base 4 of x plus 1 is equal to log base 4 of 25. Now, similar when we have the same base for exponential functions, we have the same base on both sides, we can cancel those out and just set the exponents equal to each other. Well, if we have log of 4 and log of 4 on both sides of the equal sign, well, it's just a function. It's like multiplying by 3 on both sides, or dividing by 3 on both sides. You can undo that on both sides. So what I'm going to do is I'm going to cancel out the log base 4 and just set my arguments equal to each other. In this case, x plus 1 is equal to 25. Subtract 1 on both sides. X is equal to 24. Leave this in exact form. So I'm going to put that into a solution set. Boom, done. Not too bad. Now let's try B, because this is where things get really interesting. So taking a look at B, I go, okay, well, I kind of want to do a rearrangement here, but I can't do that with the 20 out in front. So I'm going to take this 20 and bring this up here to be an exponent. You can divide both sides by 20, and that will work as well. However, I just wanted to practice some of our exponent rules, so I'm going to take a slightly longer route. And I also wanted to practice this log rule, because I feel like we haven't practiced this enough. So this is going to become log base 4 of x to the power of 20 is equal to 10. And now I'm going to use my rearrangement, base, answer, exponent. So this becomes 4 to the power of 10 is equal to x to the power of 20. So the way, something just popped up. There we go. The way I'm going to get rid of that power of 20 is I'm going to put this to the power of 1 over 20. And if I do that to one side, I also have to do that to the other. So let's see, 4 to the power of 10 to the power of 1 over 20 is going to be 4 to the power of 10 over 20, so multiplying those together, is equal to x to the power of 20 times 1 to the power of 20. Well, 20 times 1 over 20 is just 1, so this will be x. 10 over 20 is 1/2. And just a reminder that 1/2 means square root. So I just wanted to go through and share some of those with you. This can be done slightly quicker, but I just want to show. Anyway, we get to here and we go, okay, square root of 4 is equal to x. So x is equal to positive and negative 2. But I'm not going to include both the solutions in the solution set. I'm only going to include 2, the positive answer. And this is because, let's write a side note, you cannot take the log of a negative number. This has to do with its domain. So if you try, for instance, in your calculator right now, finding log of negative 2, it's not going to work. It's going to give you a domain error. Just really quick to remind you, if we have a graph, our a graph of log base 2 to the x has a vertical asymptote when x is equal to 0, and the graph looks something roughly like this. But that means that if I try plugging in any numbers over here, they're not going to exist because of this vertical asymptote. There's that barrier right there. So we cannot take a log of a negative number. So in this case, when we take a look at negative 2, we're going to say that negative 2 is an extraneous solution. It's my hope that you've heard of extraneous solutions before. Extraneous solutions are essentially answers that you can solve for, but don't actually make sense for the problem. So once we go through and we find some answers here, I'm going to go back and see, do these work in my problem? If I was to plug a 2 in right here, no problem, no biggie, we're good. But if I was to plug a negative 2 in here, you can't take the log of a negative number. So I always have to check. So in my solution set, these are only problems that work. So when you're solving, I want to see that, yeah, I can see that you know that you can get plus 2 and minus 2 as an answer for x, but that you also know that 2 is the only one that works. So you don't need to cross out negative 2, you don't need to erase it, you don't need to do anything like that. You just have to show me that you know that it does not go in here. So let's practice a few other problems with extraneous solutions. Taking a look at the next page, page number 6. We're going to try problems both A and B. So for problem A, I'm going to take a look here. 2 times log base 4 of x plus 1 is equal to log base 4 of 25. I want to cancel out the log base 4s like I did before, except this 2 right here. So I'm going to take this 2. I'm going to bring this over here to be the exponent of not just the 1, but the entire argument. So this is going to be log base 4 of x plus 1 squared is equal to log base 4 of 25. So then from here, yes, I have the 1 log, same base on either side of the equal sign. We can just cancel those out. We're going to get x plus 1 squared is equal to 25. And if we solve, I'm going to start by square rooting both sides. Get x plus 1 is equal to the square root of 25. So we get x plus 1 is equal to plus or minus 5. Now, I don't know if there's going to be any extraneous solutions yet, so I'm going to start solving these separately. I'm going to have one situation where x plus 1 is equal to positive 5, where x plus 1 is equal to a negative 5. So if I solve that first one and I subtract 1 on both sides, I get x is equal to 4. If I take that and I plug that back in here, 4 plus 1 gives me 5. Okay, positive, we're good. If I try that with my other one, so we get x is equal to a negative 6. If I take that negative 6 and plug it back in here, negative 6 plus 1, oh no, that's negative 5. You can't take the log of a negative number. So when I write out my solution set, I'm only going to put a 4 in here. So again, you don't have to cross it out, you don't have to erase it, you don't have to make a big show. Just I will be able to see, oh hey, they were able to solve for both of these solutions, but they know that this is the only one that will work. So that is what I want to see. Let's try another problem. Let's take a look at problem B. So let's see. For problem B, I have two logs of the same base being added together, so I'm going to multiply their insides. So this will become log base 6 of x plus 4 times x plus 3, is equal to 1. From here, I'm going to multiply my factors together. This will be log base 6. You can FOIL, box method, whatever you need to do. This will be log base 6 of x squared plus 7x plus 12 is equal to 1. And then here, we can't just cancel out the log like we did in the previous problem because there's not a log on both sides of the equal sign. So since there's a log on only one side of the equal sign, this is when I'm going to use my log bay, or bacon and eggs, and rearrange that. So this will be a base of 6, an exponent of 1, and we're going to set this equal to our answer of x squared plus 7x plus 12, and solve. So 6 to the power of 1 is just 6. So I'm going to subtract 6 on both sides and get 0. It's equal to x squared plus 7x plus 6. And now I'm going to factor. So I need two numbers that multiply to 6 and add to 7. And that's going to give me x plus 6 times x plus 1. So to solve for each of these, I'm going to set both of these factors equal to 0 and solve. So my first one that I get is x is equal to negative 6. And my second one is x is equal to negative 1. So both of these answers are negative, but it doesn't necessarily mean that neither of them is going to work. It is possible to have a no solution, but let's go back and see. So if I take this negative 6 and plug into here, negative 6 plus 4 is negative 2. Okay, negative, not going to work. Negative 6 plus 3 is negative 3. Okay, negative, not going to work. So I know negative 6 is an extraneous solution. And again, you don't have to write this, but I'm going to just so that we can kind of see and know. If it helps you to write that down, you can if you like. And then if I try this negative 1, if I take negative 1 and I plug it in here, negative 1 plus 4, oh, that's just 3. Okay, that's totally fine. Negative 1 plus 3, oh, that's positive 2. That's also okay. So I can see that even though both of my answers are negative, x can be negative 1, because if I went and I plugged that back in, I'm still taking the log of positive answers, and that's okay. So now that we've practiced a little bit with extraneous solutions, let's just do one more problem. We're going to skip page 7, go all the way to page 8. We're just going to go over problem A and be done. Or probably example 10A and be done. So there's a few different methods that we can do for this problem. We can change that 1 into something with a log. However, we can also move all the logs so they're all on the same side of the equal sign. So I'm actually going to be solving this problem twice just so that you can see the different solutions. The very first thing I'm going to do is I'm going to add log base 5 of x minus 1 to both sides. So this will be log base 5 of x plus 3 plus log base 5 of x minus 1 is equal to 1. Okay, so this is the first way, is moving all the logs to one side. I have two logs of the same base being added together, so I'm going to multiply their insides. So it's going to be log base 5 of x plus 3 times x minus 1 is equal to 1. I'm now going to multiply that together, FOIL, box method, whatever you need to do. You're going to get log base 5 of x squared plus 2x minus 3 is equal to 1. And then from here, we are going to use our rearrangement because now we only have logs on one side. So that's base answer exponent. And this is going to be 5 to the power of 1 is equal to x squared plus 2x minus 3. And this is starting to seem really similar to our last problem. So 5 to the power of 1 is just 5. I'm going to subtract that on both sides. We get 0 is equal to x squared plus 2x minus 8. I'm now looking for two numbers that multiply to negative 8 and add to 2. So this will be x plus 4 and x minus 2. I'm going to take each of these factors and set them equal to 0. And when I solve, I get x is equal to negative 4 and x is equal to 2. So if I go back and I plug these back into my equation, if I take negative 4 and I plug it back in here, negative 4 plus 3, oh no, that's negative 1. That's not going to work. Can't take the log of a negative number. But if I take 2 and plug it in here, 2 plus 3, it's going to give us 5. Okay, we're good. And if we do 2 minus 1, okay, we're still good. So in this case, our answer is going to be just 2. because -4 is an extraneous solution. But let's try this another way. So the other way to do this problem is if we change 1 into something of log base 5. So if we have log base 5 of x plus 3, I'm using a different color for each of the different problems. So log base 5 of x plus 3 is equal to, if you remember yesterday, we said when the big base and little base, or the base of the log and the base of the argument, were the same and there was no exponent, we knew that was equal to 1. So we can change this to log base 5 of 5, because we know that the 5 inside the argument has an exponent of 1. And if we were to go backwards to cancel those out, that's going to give us 1. And then we will leave that with minus log base 5 of x minus 1. So this rule right here is just going backwards on a rule that we've been using a lot. So now that we're here, I'm going to simplify this side of the equal sign. I have 2 logs of the same base being subtracted from each other, so let's divide their insides. So this will be log base 5 of x plus 3 is equal to log base 5 of 5 over x minus 1. And then from there, I have 2 logs of the same base on either side of the equal sign. There's only 1 on each side. And just like what we've done previously, I can say, you know what, I'm going to cancel these out, just like I would the bases of an exponent. And we're going to be left with x plus 3 is equal to 5 over x minus 1. In order to get rid of that fraction, I'm going to multiply by x minus 1 on both sides. And we're going to get x minus 1 times x plus 3 is equal to 5. And then you'll start to notice this looks very similar to our other way of doing this. So I'm going to multiply my factors together and get x squared plus 2x minus 3 is equal to 5. I'm going to subtract 5 on both sides. So we have x squared plus 2x minus 8 is equal to 0. Again, I'm going to factor and get x plus 4 times x minus 2 is equal to 0. I'll set each of these factors equal to 0. And we get x is equal to -4 and x is equal to 2. We already know that -4 is an extraneous solution and 2 will work. So we'll put that into the solution set. So either way you decide to do this will work. Pick your favorite. Both are equally valid. So like I said, this is more practicing. The only new thing we learned in this video was about extraneous solutions. So send me emails if you have any questions, and I look forward to seeing you on Monday.